Ever been totally stumped trying to hang a picture because you weren't quite sure if that nail was level?
Oh, yeah. Or maybe you've tried to follow a map where the scale felt completely off.
Exactly. It's those little everyday moments where we kind of bump into the fundamental importance of getting things
Yeah.
well measured right.
Absolutely. Measurement is, so woven into the fabric of our daily existence that we often don't even think about it.
Until something goes sideways.
Right, until it goes wrong. It's really the silent language of accuracy.
And that's exactly what we're plunging into today on this deep dive. Forget wading through dense textbooks. We've sifted through a whole stack of educational materials to bring you the core insights on measurement. Think of it as the cheat sheet to understanding this essential part of how we interact with the world.
Our goal today is pretty clear, I think. We want to explore why measurement is so indispensable.
Yeah.
And trace the fascinating journey of how we've come to measure things the way we do, and really nail down the standard systems that underpin modern life.
We're after that aha moment,
Yeah.
making the complex clear and giving you, hopefully, a fresh perspective on the world around you.
Definitely. We've looked at everything from basic science primers to the real nitty-gritty of international standards.
And it makes you wonder, doesn't it? Have you ever really paused to consider why a liter of milk here is the same as a liter practically anywhere else?
Or how we went from using, say, the length of someone's foot, which is obviously variable,
Right.
to these incredibly precise systems we have today. Let's get into it.
Okay, so let's kick things off with the big question. Why bother measuring at all? Our sources are, well, they're brimming with everyday examples that really highlight its necessity.
Think about it when you're buying something like rice. You ask for a specific weight, right? A kilo, half a kilo.
Yeah, and that measurement directly translates into what you pay. Or consider how doctors track a child's development.
Those height and weight measurements are vital clues to their health and growth.
And even something as, fundamental as getting clothes that fit properly relies entirely on a tailor taking accurate body measurements, a point emphasized in our materials.
Definitely. And it goes beyond just transactions and tracking. Measurement gives us a shared reality, a way to avoid making purely subjective calls.
Ah, like that example one of our sources used. 2 lines drawn on a page might look different in length.
Right, your eye can be fooled.
But when you actually measure them, they can be identical. It's about moving beyond just guesswork.
The same applies if you're trying to share juice equally between glasses without measuring. It's just an estimate, isn't it?
Right. Our sources define measurement quite simply as comparing something unknown to a known fixed amount of the same thing.
And this brings us to the idea of a physical quantity, basically anything in the world that can be measured.
Yeah, we're talking about things you encounter every day, like how long something is, length,
How much time has passed.
time,
Yeah.
how much space something takes up, which is volume.
Or how hot or cold it is, temperature, all physical quantities.
And these physical quantities aren't all on the same level, are they? We have what are called fundamental quantities.
Exactly. Think of these as the basic building blocks of measurement. They stand alone. They don't depend on measuring anything else first.
Okay, so like mass, length, time, and temperature. Those are key examples our sources point to. They're independent.
Precisely. Then you have derived quantities. As the name suggests, these are built by, combining those fundamental quantities.
Right, like area you need to measure, length and width, both fundamental lengths.
For density, which combines mass and volume, and speed. That's a relationship between distance, which is length, and time.
Got it. All these are derived quantities highlighted in our materials.
This leads us straight to the crucial idea of a unit. A unit is simply that standard way of comparing things we mentioned.
But if we look back historically, this is where things got a bit chaotic.
Oh, definitely. Imagine trying to trade goods when your idea of a foot was, literally your foot, and different from the person you were trading with.
Yeah. Our sources detail some of these early, shall we say, less precise units for length. We're talking about using your actual footstep.
Right. Or the length from your elbow to your fingertips. That's a cubit.
A cubit, yeah. Or the span of your hand when you stretch your fingers out. A hand span. People even use things like ropes and sticks, apparently.
And as one of the activities in our source material brilliantly shows, these methods were just inherently unreliable.
How so?
Well, if you measured a table using your hand span, and then someone with bigger hands did the same, you'd get a different number of hand spans.
Ah, of course. It's like trying to describe a color. It's subjective. This inconsistency must have made early trade and construction a real challenge.
A huge challenge. So the invention of rulers with standard mark units was a total game changer.
Right, suddenly, if two people measured the same object with different rulers that had the same markings, they'd get the same result. Consistency.
It all boils down to having that universally agreed upon yardstick, so to speak.
And our sources make it really clear that a measurement isn't just a number floating in space. It has to have a unit attached to it to make sense.
Yeah, there's this little formula. Quantity Q equals a number N times a unit U. Q equals NXU.
So 10 meters clearly tells you the amount, 10, and the type of measurement, meters of, say, cloth.
Exactly. Similarly, 15 kilograms gives you the quantity and unit for something like sugar. Both pieces are essential. You can't just say 10. 10 what?
10 what exactly. So we see why having standard units is so important now. Let's maybe explore how these standard systems actually evolve.
Okay. Our materials trace this historical path, starting with those fundamental quantities we talked about: length, mass, and time.
Right. We saw the development of systems like MKS.
MKS, yeah. Meter for length, kilogram for mass, and the second for time.
Then there was CGS.
Centimeter, gram, second, a smaller scale version, really.
And even FPS, which some of you might still encounter in certain contexts, using the foot, pound, and second.
Right. These were all significant steps towards bringing some order to measurement, getting people on the same page, more or less.
But even so, while MKS gained a lot of traction, having multiple systems still created headaches, didn't it? Trying to compare information across different scientific fields or even different countries.
Absolutely. Which is where the SI, or Système International d'Unité, steps onto the scene. In 1960, it was officially adopted to create a truly global standard.
The international system.
Exactly. And it's crucial to understand that SI units are, by definition, standard units agreed upon internationally to ensure we're all speaking the same measurement language.
As our sources put it, a standard unit is one that can be used everywhere as the basic building block for measuring a particular quantity.
And the SI system isn't just about those big three length, mass, and time. Table 1.1 in our materials actually lays out the 9 fundamental units of the SI system and their abbreviations, their symbols.
Okay, let's see. We've got length in meters, mass in kilograms, time in seconds.
Temperature in Kelvin K, which is the standard scientific scale, different from Celsius or Fahrenheit.
Right. Then electric current in amperes.
How bright something is luminous intensity in candelas CD.
And the amount of a substance, chemically speaking, in moles.
And beyond those 7, the SI also includes units for measuring angles. The radian, rad for flat, 2D angles.
Yeah.
And the steradian for solid angles, think of the angle formed at the point of an ice cream cone.
Ah, okay. So those 9 form the bedrock of how we quantify the physical world in a consistent way.
That's the idea. But just having these standard units isn't the whole story. There are also specific rules, almost like a grammar.
A grammar for units.
Yeah. For how we write these units and their symbols to avoid any confusion, our sources are quite clear on these conventions.
Okay, like what?
Well, for example, the symbols for most units are written in lowercase letters. So it's kg for kilogram, m for meter, eds for second. The exception is when the unit is named after a scientist. In that case, the symbol starts with a capital letter, like A for ampere, after André-Marie Ampere.
Or N for Newton, K for Kelvin.
Exactly. It's a nice way of giving credit where it's due. And degrees for Fahrenheit, although that's not SI.
Gotcha. What else?
Another important rule: no full stops, no periods after the symbol, unless it's actually at the very end of a sentence, just regular punctuation.
So 10 kilograms, not 10 kilograms with a period.
Right. And this is interesting. The symbols don't change in the plural. It's always 20 meters, never 20 meters.
Okay, but you'd say 20 meters if you wrote it out.
You would, yes. When you spell out the full name of the unit, you do use the plural form 10 kilograms, 20 meters.
And also, when you write the full unit name, like Kelvin or Newton or meter, it always starts with a lowercase letter, even if it's named after someone.
Correct. Unless it's starting a sentence, of course. And finally, when we deal with derived units that involve division, like speed distance divided by time, we use negative exponents in the symbols. So meters per second becomes scythe.
Meters times seconds to the power of -1. Okay. It's all about maintaining clarity and precision, isn't it?
Exactly. Consistency is key.
It's fascinating that our sources mention the National Physical Laboratory, the NPL, in New Delhi. They play a vital role in maintaining the national standards for all these fundamental units right here in India.
Yeah, it really underscores the importance of having a central authority, a reference point, to ensure accuracy and consistency across the board.
Okay, so we have these fundamental SI units, the rules for writing them, but they're not always the most convenient for everyday use, are they?
No,
Yeah.
definitely not. Imagine trying to describe the distance between, I don't know, London and New York in meters. It would be a ridiculously large number.
Or the size of a speck of dust in kilograms.
Exactly. That's where the idea of multiples and submultiples of units comes in super handy.
Right. For really large quantities, like the distance you might travel on a road trip, using kilometers is much more practical than dealing with millions of meters.
And a kilometer, as our sources remind us, is a multiple of a meter. 1 kilometer is simply 1,000 meters, or 10 to the power of 3 meters. It just makes the numbers more manageable.
Makes sense. And conversely, when we're dealing with tiny things, like, say, the thickness of human hair or the size of a microchip,
Then we need units smaller than the base unit. Centimeters, millimeters, even micrometers. Those are submultiples.
our materials give the standard conversions. 1 meter is 100 centimeters or 1,000 millimeters.
Right, and even smaller, a micrometer is 1 millionth of a meter, 10 oberters.
Our source gives a good example. The diameter of a coin might be, say, $2 times 10 to 2 meters, which is perfectly accurate SI.
But sounds a bit clunky, yeah.
It's much easier for most of us to picture that as 2 centimeters, right?
Absolutely. Table 1.2 in our materials provides a helpful overview of common multiples and submultiples for both length and mass, with their prefixes like kilo, centi, milli, micro, mega, giga.
Very useful.
It's also worth noting that some older units that aren't officially part of the SI are still widely used. Things like yards, inches, pounds, feet.
Still hear those a lot.
Yeah, and for practical purposes, they're defined precisely in relation to SI standards now. So an inch is exactly 2.54 centimeters. A pound is about 0.45 kilograms. Our sources detail these conversions.
So it's kind of a nod to the history of measurement while still maintaining that connection to the modern standard.
Pretty much. And for a real-world example, example 1 in our source shows how to convert a distance given in meters, say Tanu School is 300 and 250 meters away,
Okay.
into kilometers. You just divide by 1,000, giving you 3.25 kilometers. Simple conversion.
These conversions are just an essential skill in navigating different contexts and information, aren't they?
Definitely need to be comfortable with them. Now, shifting our focus to the extremes of scale, our sources also touch on specialized units we use when dealing with the incredibly vast.
Like space.
Exactly, or the unbelievably tiny. For instance, when we talk about the distances to other stars and galaxies, kilometers become, well, laughably inadequate.
The numbers just get too big.
Way too big. That's where the light year comes in.
Ah, yes, the light year. Not a measure of time, despite the name.
No, definitely not. It's the distance light travels in 1 year. And our materials tell us that's roughly $9.46 times 1012 kilometers. 9.5 trillion kilometers, basically.
Wow. It's almost impossible to wrap your head around that number, but it's essential for talking about cosmic distances, I suppose.
It puts things on a manageable scale, relatively speaking. Then on the opposite end of the spectrum, for measuring the sizes of molecules, atoms, tiny biological structures,
Things we can't see.
right, we need incredibly small units like the micron, which is another name for a micrometer.
Okay, 10 meters.
Then the angstrom, A, which is 10 meters, often used for atomic sizes.
And the nanometer. It's very relevant these days with nanotechnology.
Extremely relevant. That's 10 millimeters, a billionth of a meter. These units allow scientists to work with numbers that aren't, strings of dozens of zeros when exploring the fundamental building blocks of reality.
Keeps the maths tidier. Okay, so finally, let's circle back quickly to derived units.
Right. As we discussed earlier, these are the units we get by combining fundamental ones. Our sources include a really useful Table 1.3 that shows some key derived units, the formulas used to calculate them, and their corresponding symbols.
Okay, so we see how the unit for area, which is length times width, is the meter squared.
And volume, being length times width times height, gives us the meter cubed.
Speed, as we've touched on meters per second, ems or emso.
Density, which tells you how much mass is packed into a certain volume. That's mass divided by volume. So it's measured in kilograms per cubic meter, kilogm or kilogram mu.
Right. The table goes on to list other crucial derived units like acceleration.
Meters per second squared, ms, the rate of change of velocity.
Force, which we measure in newtons and is fundamentally kilograms for.
Sure, Professor. Yeah.
Velocity, also in ems, but with direction implied. Work and energy.
Both measured in joules, J, which is defined as a Newton meter.
And power, the rate of doing work, in watts, W, which is joules per second, Amos J.
Mhm. Even potential energy is shown to have the unit of joules, just like work and kinetic energy, highlighting the interconnectedness of these concepts through their units.
It's amazing how this web of interconnected units really demonstrates how our understanding of the physical world builds from those fundamental measurements we started with.
It's a remarkably coherent and logical system, isn't it? It allows us to describe and quantify everything from the smallest particles to the largest structures in the universe with a shared language.
So to kind of bring it all together in this deep dive, we've journeyed through why measurement is so critical in our daily lives.
From cooking to construction.
Explored the fascinating evolution from, well, inconsistent local units to the globally accepted SI system.
That drive for uniformity and accuracy.
And highlighted the practical importance of understanding prefixes, multiples, submultiples, and how derived units are formed from the fundamental ones.
We hope this has maybe illuminated a topic that you likely encounter every single day, perhaps without giving it a second thought.
Yeah, grasping these fundamental principles provides a powerful foundation, not just for understanding scientific information, but also for navigating the world around you with, hopefully, greater clarity.
And avoiding those everyday frustrations caused by measurement mishaps, like that wonky picture frame.
Exactly. And on that thought, here's something to really chew on as we wrap up. Consider how different fields of study, from the vastness of astronomy tearing across billions of light years,
Using those light years we talked about,
to the precision of nanotechnology manipulating matter at the nanometer scale,
relying on nanometers and angstroms.
all depend utterly on the precise and consistent application of these fundamental and derived units we've discussed. So the final thought is, what entirely new frontiers of discovery might become possible in the future with even more accurate and refined ways of measuring the universe?
That's a big question. It really makes you think about the limits of our current knowledge and how measurement pushes those boundaries.
It's a thought that stretches far beyond just getting that shelf to fit or baking the perfect cake, isn't it?